The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon. I'm John Stoltz, Director of Conferences and Events at APICS. Thank you for joining us today for our webinar, Cognitive Supply Chain, Artificial Intelligence Today and Tomorrow. Please be sure to mute your computer microphone and phone during this webinar. We will begin shortly. At the end of the presentation, we will save time for a question and answer session. If you look at the toolbar on the right of your screen, you'll see a questions box. To ask your question, simply type it in the box and select Send Question to Staff. You can do this at any time during the presentation. In addition, this online event is being recorded. We will post the presentation on our YouTube channel and will email the link to everyone who is registered for this webinar. Should you experience any technical difficulties during today's broadcast, please contact GoToWebinar Tech Support at 800-263-6317 for US and international at 1-805-617-7000. We're pleased today to be joined by Al Naqvi, CEO, professor, and researcher at the American Institute of Artificial Intelligence and a global authority on applied artificial intelligence in business. Specializing in making AI learning easy for business executives and democratizing artificial intelligence, Al has developed 12 courses in applied artificial intelligence in strategy, finance, marketing, supply chain, human resources, and more. He was the subject matter expert on the first introductory courses developed in robotics and artificial intelligence. Please join me in welcoming Al.
Thank you. And thank you to all the audience members. Please, feel free to ask questions at the end. The goal is today to introduce cognitive supply chain and also a few concepts about machine learning and blockchain. So what we will cover today is what is cognitive supply chain, or CSC, what is machine learning and how it's impacting business, and what does the cognitive revolution really means for business professionals, and how can we get ready for what lies ahead. So supply chain saga continues today. It started in 1980, and we have gone through tremendous amounts of money that has been invested in this field, from supply chain management to strategic sourcing and the internet-based supply relationship management, vendor managed inventory. So we've gone through so many different models. But even in 2017, when you interview people, one of the things that you hear is that our problems continue. Supply chains continue to be expensive, risky, the risk has gone up, the insecurity has gone up, suboptimized, inflexible, and inefficient. So the question is why? Well, throughout these last 35 or so years, we have understood a lot of things about supply chain that we didn't know before, and it's natural for us to develop linear solutions as we have done in the past because of our relative low-level understanding of supply chain. So supply chain is a network. That's one of the things we learned, which implies that it has lots of nodes, which actually nodes represent agents, and these agents are all maximizing their own gain, and they have relative independence from each other while they're maximizing their gain, but they're also part of this large network, so there are interdependencies between them, and then these links between them are really interactions such as transactions, relationships, and which forms the entire network. The second lesson we learned is that a complex system really, that supply chain is really a complex adaptive system, which means that it is has large number of elements which are part of arranged structures. These elements interact locally, but every element directly or indirectly is connected to every other element. And as things change around, you cannot really explain them by a single rule or reducible to a single simple explanation. And sometimes new features emerge which are not really predictable. And the adaptive system dynamics also implies that when that a system itself experiences change when its environment changes, but it attempts to stay in some level of invariant state. It wants to maintain that. Which also implies the third lesson we learned is that this emerging system, or it's an emergent system with self-organizing dynamics, which means that local interactions lead to a global pattern of behavior, but system increases its own organization. And emergent properties are that, again, makes the system sort of unpredictable because the behavior of the whole cannot be predicted simply from parts. So because it's a result of nonlinear combinations. The fourth lesson we learned is through this entire network, we can actually look at a product or service that forms the unique path through this. So these dots are connected through a product that moves through this value chain or through this network of supply chain. And it also determines the entire length or range of the supply chain. So the point of origin, all the way going back to the raw material resources, to all the way end of the product when it's completed or it has done with its life cycle. So these are, and the fifth thing is that we have learned is that physical movement of product is not the only thing that we need to be concerned about, but also we need to concern ourselves with financial value chain, or how money moves through the system, regulatory support structures, and how information flows. So when you look at a supply chain, it's not just physical movement of products, but all of these things that are that go with it. The sixth lesson we have learned is at any given point in this network, an agent who is trying to maximize his or her payoff, it typically has a very local viewpoint, and cost of looking beyond the focal range becomes very high. So you can look a little bit upstream, you can look a little bit downstream, but going beyond that, it becomes very expensive to do that. Some of the recent experiences, so besides these lessons that we have learned in 35 years, some of the recent experiences are that complexity it has increased tremendously of our supply chain. New products and rapid innovation is going on. Product life cycles are very small at this point, and innovation is taking place not just on the product side, but also on the financial product side. Regulatory developments are happening, as well as new CSR requirements. New types of customers are emerging, and new clusters of partnerships and alliances form, and then they quickly dissolve and dissipate as companies move to another product or another customer base. Other things we're learning now, new dynamics, are that competitors can come from any unexpected left field that you wouldn't anticipate a competitor to come, and business models obviously have new business models that are being deployed to compete with you. And one bad decision, for example, Samsung battery, can really impact the entire firm. And we are also exposed to new kinds of threats such as cybersecurity, physical, and terrorism. Another recent experience is that our supply chain cuts through across sectors, so it extends beyond the focal sector within which supply chain dynamics used to take place. And also another recent experience is that we have to be extremely responsive because customers are very active and they want instantaneous response. Also, the dynamics of supply chain are constantly evolving and changing, which includes the essential structure of the supply chain also. So optimizing such a complex system is very hard because there are just too many variables at work, and there are too many constraints that you have to deal with. the system becomes has unpredictable because of its essential dynamics, and dynamics change rapidly, and change itself becomes unmanageable. So the questions to consider is that how can we achieve local optima at almost every level in the supply chain while achieving a global optima simultaneously? How can we optimize this dynamic supply network? And how can we address problems of supply chain management as we are trying to optimize? So as we talked about, that there is not just one problem. There are many areas, for example, flexibility, security, safety, all of those things that we need to consider. So what appears to be solution that's emerging is that we have to start thinking on a decentralized optimization and execution basis. So as much as we would think that we can capture all the information in a supply chain in a centralized manner, the solution seems to be more, and the key word being decentralized here. We also have to move from limited awareness to high state of awareness, and you can see that these two things are at conflict with each other. When you don't have centralized planning, you would think that it will be hard to get to a high state of awareness. And the third thing we need to do is to move from non-learning state to learning system, and which is the essence of this cognitive revolution, as well as cognitive supply chain, is to be a learning system. So essentially, cognitive supply chain is composed of three things. Number one, it's autonomous. It's self-adjusting, which means it's without any human intervention, and it responses to the demands of requisite changes. Second thing is that it anticipates value vectors and even problems before the actual state when an impact to a supply chain or supply chain becomes vulnerable. It understands that beforehand and hence preemptively intervenes. It adjusts, adapts, and self-heals. So it has both sides to it, being predictive as well as being prescriptive, and being able to fix itself. And it also operates in a high state of awareness, which is achieved via something known as deep reinforcement learning. So a supply network really, again, just to summarize in cognitive supply chain terms, is composed of nodes, which are actors attempting to maximize their value, links that represent the interactions between these actors, and the nodes themselves do not create the emergence part, the interactions between the nodes do. So transactions and buying and selling, transfer of goods, those are the things that create the emergence of the system. It can be managed as a decentralized system, so there is no central control which is regulating the system, and focal boundary does exist. However, awareness about the forward and backward or upstream and downstream is possible, primarily through learning, machine learning. And the value vector is the successful outcome or the expected successful outcome of what you desire, what you expect the performance of the supply chain or the system to be. So decentralized being the key word, you can think of it as from human control to fully autonomous on one end, and from a decision tree based or old style optimization, which would go through every possible path in a network, to a deep learning model. And this circle, the yellow circle up on the top right, represents the state where we need to get to, and that's the cognitive supply chain, which is composed of decentralized autonomous agents that adapt, anticipate, and adjust to all types of challenges while simultaneously optimizing the success of the system. So what is this deep learning thing, and what is this deep reinforcement learning? And you know, and I assuming that the audience members are not machine learning experts, since this was a business presentation and supply chain focused presentation. So I think it's worth it, since we hear this word a lot, machine learning, and we hear so much about what's happening in artificial intelligence. One of the things that we have done is, as John said, is to democratize AI, which means to make it simple enough so that everyone can understand at least the basics. And I am talking about the business people to be able to understand the basics. So this part deals with at least, you know, developing the conceptual framework for what machine learning is. So things have progressed a lot in machine learning. In 2011, on Valentine's Day in February in 2011, IBM Watson did that Jeopardy thing, in which you know, it beat the other two contestants simply because this system was based on artificial intelligence, and it fascinated the world. In 2015, AlphaGo it played the first formal match against the European, 3 times European champion in October of 2015, and it won by 5-0. Now, in the next slide, I'll explain why this is a huge and just unbelievable development between 4 years. But for now, in 2016 again, Lee Sedol, who was a winner of 18 world titles and considered to be the greatest player of the past decade, AlphaGo won by 4-1 in Seoul, South Korea. And in January 2017, a newer version of AlphaGo, it played an online fast-paced game and had scored straight wins of 60 times. And AlphaGo Zero, which they're launching, I believe, this month, is an advanced version of that. And it's again, it's teaching itself. So it started completely randomly playing the game with itself and started learning on its own without even human intervention at this point. So why it's such a big thing is that there are in the game Go, unlike chess, it is far more complicated. It's 10 to the power of 170 possible board configurations. This is more than the number of atoms in the known universe. So, which obviously makes it an immensely complex than chess. So any regular deployment of optimizing this would not work, because one would have to look at every possible move. So tree searches may not be the right solution for that, and that's why deep neural networks came out as a possible solution, in which was combined with something known as reinforcement learning, and we will consider that in a second, what that is. So the difference between programming and machine learning is, think of it this way, that programming is giving a fish to a person. In programming, you write line by line code and you tell the machine to do something, versus in machine learning, you teach the person to fish, which implies that instead of writing line by line instructions, you can give it an algorithm that can help it learn and do the task on its own. So machine learning is essentially learning from data and predictions in our decision to make predictions and our decisions. Intuitively, it represents the ability to teach machines to use data to form some kind of conclusions. So how does it happen? we teach machines to learn from their experience, and machine learning algorithms, they don't rely upon any predetermined equations, because that will not be learning, that will be programming. So the difference being is that you teach the machine to learn on its own, as well as performance of the algorithms is generally, it becomes better as more sample or data samples are provided to the machine. So algorithms can discover natural patterns within data and develop insights and predict the unknown to help you make better decisions. So how does it do that? For example, if I give you this data, you can predict just by looking at the data that the second number is the square of the first. So the last one with the question mark should be 81. So this is this is exactly, you found a pattern in data, and you were able to predict that. Now, how does that happen? So there are three types of learning at this point that we use. One is supervised, in which you know the outcomes, you have labeled data, you know the outcomes, and between, this is the right outcome or wrong outcome, and you have the input data and you have the output data, and and you can train the machine with the based on the knowledge that you have about the output, pre-existing knowledge about the output. So, and then you have unsupervised, where there is no labeled data, which means that there is machine has to figure out on its own without knowing the right answers, and it has to predict what the right answers are. And the third type is reinforcement, in which learning, in which essentially is a method, think of it as a trial and error, in which evaluative feedback is given, but no supervised signal comes back. So it makes a mistake and it learns from that. So supervised learning is finding patterns and develops predictive models using both input data and output data. You know the right and wrong answers, as I mentioned before. There are two types of them. One is classification and one is regression. Classification is used for predicting very discrete responses. For example, is this email a spam or not? So you tell the machine what the spam is and what it's not, and then machine learns based on that. And regression is used for finding trends, and for example, trends in demographics, stock prices, weather forecasts. Unsupervised learning is essentially, think of it as cluster analysis. So data with similar features tends to cluster around similar other data with similar features, and you just keep feeding more data to machine, and it starts learning that these clusters are forming, and it finds patterns based on input data, which is not labeled. So this technique is useful when you're not sure what to look for, or you don't know the answers, right versus wrong answers. So it's often used for discovery and exploratory analysis of raw data. Now, one of the very interesting things that is coming out is neural network, and the reason it's important to understand that for business people is because a lot what would be happening in our world as we go forward will be based on this knowledge that we are being exposed to today and what business is being exposed to today. Neural network is very much based on how human brain functions, at least at a concept level. So we have, for example, neurons that transfer information from one neuron to another neuron. For example, a sensory neuron will take information if you touch a hot surface and will provide that information back to a motor neuron, which will take the action. Now, the things that are important to consider here is that the neurons are connected, so there's some level of connection. Second thing is there's strength of connection, so that means that the sensory neuron was able to activate enough and so that it could transfer information to motor neuron. So this can actually be modeled for example, that of a neural network is that, let's say Homer, we can make him salivate because he likes burgers. And by saying that when we expose him to a burger, which will become firing of a neuron of value 1 by a weight, because that is something that he finds the stimulus to be attractive. So 1 times 1 will give it 1, and 1 means he will salivate. Stimuli times weight. However, he doesn't like soda. So in this case, even though he's exposed to soda, a neuron will get fired, which means the number is 1, but its weight is 0 because he doesn't like it and he will reject it. So how can we make Homer like soda? How can we make him to learn about soda and appreciate that? Well, one thing we can do is by conditioning Homer is we can put 2 things at the simultaneously. So we can give him, time 1 soda and time 2, which without much interval in between them, and time 3, Homer just looks at the burger and he responds and he salivates, but he's not looking at the soda, even though it's being presented simultaneously. So conditioning Homer in a neural network sense will look like something like this, that both things are being exposed. So both neurons are firing. However, the burger with which he can, the stimulus that he understands will have a weight of 1. So he is salivating, but he is ignoring the soda, even though it's coming in, its weight is 0. And they're both being presented at the same time. But if we start changing the weight of soda a little bit, we adjust it to, let's say, 0.25, some level of learning happened. However, 1 is the number at which he will salivate, so it's still not enough for him to respond to soda. He's still responding to burger. Well, we can keep increasing it to 0.50 as we go through iterations of training, and the weight increases a little bit because we can play around with this weight, and then we increase it even more to 0.75, and then we increase it to 1. As soon as it increases to 1, and we can remove the burger now, however, he has learned now, Homer is now conditioned to respond to soda. So we just trained him to respond to soda. Now, one of the examples, and I know it's lunchtime, so a lot of people could be very hungry, and I'm showing all these things to you, but let's say we're designing an application to pick the vegetarian meal. So there are 4 choices. It can pick the first one, or it can pick the second one, or it can pick the third one, or it can pick the 4th one. And we know that the 3rd answer is the right answer. So we can design a very high level, we can set up a high level neural network. In this network configuration, it's very simple. We have 4 inputs, and we will assign weights to them. At this point, weights for all of them are 0. And the result is 1 if it is a vegetarian meal, and it's 0 if it's not a vegetarian meal. So we start the system with 0, 0, all are zeros. At this point, no neuron has been fired. Let's say we pick the first one. When we pick the first one, it gets fired, and the firing value is 1, but the weight is still 0. The output in red number is still 0, and then since it's the wrong answer, the green number is also 0. At the bottom, we calculate what's known as error, which is the difference between the desired output and the neural net output, and that number is 0. However, we know that the answer is wrong. We do the same thing with steak, and the same exact thing happened. Wrong number chosen, and wrong answer came out, and the error is 0. However, when we pick salad, we know that this is the right choice, so the desired output comes out as 1, but the weight is still 0 of that because it hasn't learned yet, and that's where we can come in and start changing the weight to, let's say, 0.2, And at this point, the error goes down from 1 to 0.8. 1 minus 0.2 because the weight is now 0.2. We increase that to 0.4, increase that finally to 1, and that's where the error is 0 and the answer is right. And finally, it knows the right answer. And that's how machine learning, just as Homer learned to condition himself, this is exactly how a machine learned to about how to pick the right choice. Now, in between, as you can see, there's input layer and there's output layer. In between, there is something that's known as layer in between the input and the output. And what happens in deep learning, what you just saw, and I'll go back again, what you just saw was a real neural network. It was basic, but together we just saw an actual neural network in operation. What deep learning is essentially, it has many different layers in between. So, and it can have thousands, even millions of neurons. So it's a very deep network, and it has input layer, obviously an output layer, as you see in the diagram, and it can have multiple hidden layers in between. So this allows learning to be pretty comprehensive and deep. Now, reinforcement learning, which is another thing that was simultaneously developing, is with it's with the trial and error. So, for example, if you release a mouse in a maze, it will eventually find its way. Keep on doing it over and over again, it will eventually find the right way. So it will make less and less mistakes. So in this reinforcement learning, an agent interacts with the environment. It learns what the optimal policy is usually, and it does that by trial and error. So the biggest thing that happened in our world today in the last few years is, in fact, in the last 2 years, is the combination of reinforcement learning and deep learning. In fact, David Silver, who was the major contributor to AlphaGo, he made this high-level formula, which is very cute, is he's saying that artificial intelligence is really reinforcement learning plus deep learning. So we just went through and we talked about what a neural network is, and you understood that what a deep learning environment is, and then reinforcement learning. If you can somehow put these two together, you can create extremely powerful systems enough to be able to drive a car, autonomous car, to be able to scan an image and understand exactly what we're talking about. So let's go back to business side now that we have covered some of the high-level things on the machine learning side. So the model, we call it saddle model, that we have developed. It's essentially, if you think about an agent, what it's doing is it's doing 5 things. It's sensing inputs from its environment. It's analyzing its environment. It's making decisions. Then it's taking some kind of an action. And then it's learning from that action. It's evolving and it's managing its state. So the level of learning, the scales show that you can have an agent that is very good in sensing, but not too good in analyzing, deciding, acting, or learning. Acting could actually be, taking an action could be 0. Or you can have an agent that's very good in this, in all of those 5 things, because you want it to be. So there are different variations of agents that come in. But essentially what saddle model tells you is that an agent's job is to sense, it's goal-directed behavior, analyze based upon the goal, and decide, make decisions, take actions, learn, evolve, and manage its state. Now, these agents are not just alone. They talk to other agents also. The other agents could be another machine. It could be a human. Also, they can be part of physical environment if it's a robot, and also obviously entropy and randomness can impact them. So these are actually social agents. So they can compete with each other. They can cooperate with each other. They can collaborate with each other. And then as complex system dynamics unfold, as in a supply chain, they can adjust accordingly. So these interactions with each other, those are the forces that are produced and captured and analyzed and can be acted upon collectively in a supply chain to optimize the entire supply chain. So essentially, we have two types of machines at this point in AI, software agents, which reside in your computers or on the internet. They can be intelligent and they can automate simple repetitive tasks, but they can also perform very complex tasks such as trading. You can also have robotic, and obviously you have robots, which were at one point purely mechanical and remote controlled, or but now they are becoming intelligent and smarter. And even your car, autonomous car, is a robot that drives you from one point to another point. So a new revolution is taking place, and we cannot ignore it, and we cannot take it lightly, as we would see several examples coming up. This is something that is happening. It all started at Dartmouth. It was a 2-month conference that took place in the summer of 1956, and where people, professors, researchers came together, and they coined the term artificial intelligence and set the strategy for this new field. They were very powerful in terms of what they saw. Their vision was powerful, even though they were very optimistic about how they thought things would unfold. But unfortunately, things didn't go as they planned, and there were time periods that are known as the winters of artificial intelligence, in which a lot of promises were made but not delivered. There was investment stagnation that happened, and there were valid concerns about the realistic potential of this technology. But something strange happened just about 2011, when we saw this technology coming out very, very strong, real products, massive investment going on in this industry now, and hundreds of companies now exist in artificial intelligence, as well as companies themselves doing and working on these, undertaking these projects. So what changed, and why do we believe that AI spring has finally come once and for all, and this time it's different, it's not going back? Well, 4 things happen. Number one is algorithms. So we have very sophisticated algorithms, some new ones that we developed. And second thing is that we not only have tons of data now, but also we have a field known as data management, using which we can do, we're organizing data, so making it far more usable. Third thing is that we have connectivity and global connectivity, and through that, research has accelerated and a lot of sharing of information takes place. Also, it obviously generates tremendous amounts of data. And finally, we have very, very strong processing power now that we didn't have before, primarily based out of big data technologies. So an artificial intelligence platform now can be built upon that, and with a bit of serendipity, we can actually get to artificial consciousness, but we are not there yet. So at this point, we're building artificial intelligence platform based on these 4, and however, this trend is irreversible. So unlike previous times in which we were exposed to the risk of those winners, that risk has gone once and for all. And it shows because major governments are now behind this revolution. European Union published a report, USA published 2 reports, White House, and then UK published a report on this. So there are exact dynamics that are needed. China, Canada, India, Israel, a lot of these countries are tremendously advanced, in Russia in artificial intelligence, and are taking this very, very seriously. Why is it a revolution? Well, and a lot of scholars now call it the 4th industrial revolution. We have gone through 1st industrial revolution, 2nd industrial revolution, from steam engine to automobiles and electric power, to the 3rd revolution, which was information revolution, and then 4th industrial revolution. Well, if you look at these revolutions, First one, when what we call machine, first and second, in fact, both, what we call machine had fixed set of inputs, fixed set of outputs, and the internal processing of machines was extremely observable. And we had known pathways. So you could open the hood and look inside and see what went wrong, and you could fix it. Well, you know what? Same thing was true even for computer revolution or the information revolution, in which fixed set of inputs, expected fixed set of outputs. If anything didn't go right, you can open your code, you can adjust the code, but internal processing of machine was observable and known pathways existed. Well, just as you saw in deep learning just now, where there are millions of potential pathways and a lot of hidden layer processing goes on, now we're dealing with something different kind of machine. Wide set of inputs can go and we can get wide set of outputs, but in between, in the machine, these machines can learn, adapt, optimize, and they accumulate experience. And we have potentially unobservable processing, unknown pathways. So if you open the hood, you won't be able to, you may not be able to tell what's going on. This is a very different type of machine. So essentially, the definition of what a machine is has now been changed and altered. And that's why it gives you the fourth cognitive revolution. So how does it impact your work and you? Those are very important questions. So let's start looking at some examples. So Walmart and Amazon have these bots that actually, they try to get information from each other in terms of pricing information, and this battle of bots wages constantly, in which they bring back information, and based on that, they adjust their prices. This is a very powerful dynamic, if you think about that, because depending on the intelligence and the capability of the bot, your demand signal now can vary simply because of the success potential of the bot now determines whether you will get the business or not. So in terms of being from professionals, we are also observing that, we have to now, and we're really looking at the ability to engineer demand in some ways. So we have to become very much frontline charging and in some ways invasive and active versus passive, in which waiting for things to happen will not work. We see that example with the alleged Russian intervention in US elections, for example, which over 2,700 active bots, 17 million messages, and dozens of social identities that were created, which is in a way another example of forward demand engineering, in which was pretty intrusive, probably, but something that we as business people should know that if that can happen in politics, it can also happen in business. So we have to now have a strategy for backward defense engineering, protecting our firms and defending our interests if that happens. So that is something we need to be cognizant of. Then another great trend that's taking place is autonomous research and development. Discovery while you sleep. Actually, first molecules were discovered by next generation AI. This was announced in July this year. And I believe that yesterday, or the day before yesterday, NASA has announced that they discovered a new planet purely from artificial intelligence, and which was a surprise discovery. But this is an actual drug discovery taking place in a firm in silico and based out of Baltimore, Maryland, which was able to discover molecules by just using artificial intelligence. This means that discovery while you sleep implies that it's a self-discovering versus, you don't give hypothesis as is seen on the left. It's a self-discovered hypothesis by looking at the information, what we talked about before in terms of, for example, clusters. We also now Wall Street is replacing their analysts by robots, and essentially the ability to know the unknown, to analyze for unknown, fish out information that you never thought existed. And and also the ability, the speed of decision instantaneously. There is no lag in between. So you analyze, decide, and act. Another great example of that is Sentient, an investment management group based out of California, which has an autonomous hedge fund. They do autonomous trading. It's a hedge fund essentially, which functions purely out of machines. So machines make the decisions. So again, the analyze, decide, and act part happens very, very quickly, and it's happening autonomously. It has, self-guided autonomous actions are now being used in supply chain management, as well as in healthcare, and from hope in as future progresses, even in areas such as surgery. Merck has announced that AI will run demand planning for it, as well as AI being deployed for self-driving supply chain. Supply chain is, as I think we're all very, very much familiar with. So across multiple sectors, these common themes of non-permanent, fast-evolving interdependencies, which are emerging, extremely responsive supply chains, dynamic, constantly changing, is another example. And why I think that across sectors, the words are very important is when Amazon acquires Whole Foods, a technology firm, acquiring a grocery store, it just tells you the dynamics of our world are completely changing. So barriers to entry protection is no longer valid, since sector boundaries are no longer applicable. And we see that in all sectors. And for example, agriculture industry is looking to replace farm workers with robot machines. And not just farm workers, artificial intelligence is now being applied in the ag tech space for yield improvement, for understanding, when to intervene, to see pest control, instead of humans walking in the fields to see, what the problems are. A machine can take an image, scan the image, and understand the problems, and inform you. And from seeding to watering perspective, you can just, machines can manage that for you. And as Michael Porter has, in one of his articles, shown that now you're not competing against companies, you're competing against interdependent competitive systems. And also something what IBM announced, for example, H&R Block, that Watson will be deployed there, entire professions will be redefined and are being redefined. So this is a world very much powered by artificial intelligence. Blockchain on the execution side is coming out very, very strong, although still not that advanced in the supply chain management field. However, all the signs are there, that it will happen, and and they are on a test basis. It's producing good results. There's still a little bit timing thing involved in terms of the time it takes for a transaction to process, but there are approaches that are being at this point developed around that. So we will be moving from the traditional transactional universe over to blockchain universe. In terms of thinking about competitive dynamics, think about how it's changing us. We competed on the basis, for example, let's take auto sector, in which, and take one dimension of that, for example, just based on mechanical powers. And we would say this dude performed this test from how long it takes for a car to get from 0 to 60, the physical attribute of a car. So we would say that a car that takes 3 seconds is better than the car that takes 5 seconds, for instance. However, now we also have a cognitive dimension in which we say, well, which car has better autonomous features, for example, and which means that the competition has now moved. This new dimension of cognitive is now in play, which means that now we're not just competing on the basis of the traditional things that we competed upon, but also which firm has more intelligence or which product has more intelligence. So the product itself being intelligent now, you will look for competition in terms of autonomous features in a car. So needless to say that, as you saw from the presentation as well as from the examples provided, that a new era has begun. We went through Industrial Revolution 1, 2, and 3. Now we are entered the cognitive revolution. It's, today we have what's known as narrow AI, function-specific artificial intelligence, and we are not at this point, but some scholars believe that in about 2030, we will have a consciousness revolution or an AI that will become aware of itself. Hasn't happened yet, and may not happen, but at this point, we are looking at least we're 100% sure that we're in cognitive revolution. So our model for supply chain management in general should be think about blockchain, think about deep reinforcement learning. This is the model that American Institute of AI has developed. Sense, analyze, decide, act, learn. Build your machine learning and your artificial intelligence based upon your supply chain needs and features, from think about transactions, relations, how to optimize it, managing risk, flexibility, and solving problems, looking at the tools that are available to you from machine learning perspective, natural language processing, robotics, computer vision, and autonomous agents, which forms the foundation for applied artificial intelligence. So the key messages: be cognitive, which means to pay attention, stay informed, join societies in which this is for professionals who are non-data science professionals or who are non-artificial intelligence professionals, follow companies, learn concepts and reskill yourself, just as people became from, when the internet came and they shifted from newspapers to bloggers. The same kind of transition will happen. My book will be coming out in April 2018. Last is develop professional expertise, which means attending conferences, attend events, take certification and non-certification courses that are being developed and will be offered soon by APICS and American Institute of AI together. So I want to thank you, and I'll shift it back to John.
Great, thank you, Al. Very compelling content, and it's an interesting journey that you've outlined for us. We'll pause just a moment to remind everyone, if you look at the toolbar on the right of your screen, you'll see a question box. If you'd like to submit a question, simply type it in the box and select send question to staff, and we will get to as many of those as possible. We'll take a second just to tally those questions together. Okay, Al, the first question. The current civilization is at a stage where most of the information is coming through in the form of an image, be it smartphone, videos, etc. The question is, what is the role of philosophy or abstract concepts in this growing trend of using artificial intelligence?
Yeah, artificial intelligence essentially is, if you think about it, it's not a single field, it's a combination. And that's why I strongly believe that everyone has a role to play in it. And, at this point, we're at early stage, so it seems to be only, you need a PhD in mathematics and computer science to understand it, which is not true, because it is coming from, for example, neurosciences, cognitive science. Philosophy has a huge impact on artificial intelligence, not just from only from the logical side, but also from the side of how society will get impacted from this, how our culture will shape, how it will impact human civilization in general, how it will impact economy. So everyone has a role in it, and I think this field is all very, very comprehensive. It's shaped by computer science, human psychology, mathematics. Algorithms come from math departments. They came from math departments. So it's a very, very inclusive field. Unfortunately, that the doors have not been open, and that's why democratizing is important, and they're being opened now with institutes such as ours, in which we are opening the doors to bring everyone into the fold, and not just computer scientists and data scientists.
Great, thank you. Kind of following along that same line then, Al, what book or resources would you recommend to someone who is not a programmer, but just looking to, kind of deepen their understanding in this area?
At this point, I think that I would suggest that, a more online content at this point. NVIDIA and provides some very good content to understand this. And that's at a general level. If you want to go into more specific, for example, AI in marketing, AI in finance, AI in supply chain, those courses are not available yet, except us. I mean, we are doing them, but they're generally not. That knowledge doesn't exist. However, in terms of books, I would strongly suggest that if you get a general idea of this. Any type of research that you do online, even Wikipedia will give you tremendous amount of information on this field. It's all over, and IBM Watson provides tremendous amount of information. On our website, there is a scholar whom we have interviewed, and he has written a book on artificial intelligence, but the reason I'm hesitating is because it's a more comprehensive book and not necessarily for business people. But websites such as NVIDIA, Deep Learning or Google, and these IBM Watson people, they provide some very, very good information for business people.
Great, thank you. So if we're entering a period within the next 15 years where AI can consciously do any function, what areas would be safe for humans if the robots eventually are able to program?
What areas would be safe for humans?
Yeah.
Meaning professionally?
Right, I think that's the intent they're looking for. So is there a certain area that still has a critical dependency on those individuals?
Right, and my answer to this is, for example, that I was at a radiology conference just a couple of weeks ago, and a lot of radiologists were concerned about that, would it because image performance was so good with artificial intelligence, that can it just replace radiologists? And the answer to that is, and if you think about it, is that only 1 or 2 people out of 10 people have access to good healthcare. So the first thing that we will do is, it will not to take out radiologists, it will be to expand access. Same thing, that human problems have not ended. In fact, new human problems will be created. The idea is to reskill yourself and understand where this is leading you, which is important. And I give this example of newspapers and blogs. If you were still producing newspapers in 2004, 2005, there was something wrong with you, and you were not, you didn't have web presence. The idea is, when technology comes in, to shift. You didn't need to become a programmer to make that shift. You just needed to become a better user of the internet, and which implied to start blogging. So the appetite for, or the consumption for news did not change. What changed is how we consume it. In fact, if anything, the appetite or consumption for news went up. Since everyone had access to it, and that's why it's important to reskill. The key word is reskill yourself when major technological revolutions happen.
Great, thank you. And just time for one final question, Al. So what are the ethical issues and impact of this cognitive revolution?
Yeah, there are two major areas to look at. One is how the humans, as humans, how it will change us and the opportunities it will provide us to do good as well as to do bad. The second part of ethics is how to regulate or how to manage or control or govern this technology because it can autonomously do bad if it's not managed. So these are the two areas. The first one, a great example, is the alleged Russian intervention, that if it can impact the democratic institution of the world's most powerful country, what can it not do? So that's something that we need to think about very deeply, and understanding that it's important to make sure that ethical platform is developed before this technology goes out. But that had a human intention behind it. What about something that can create harm on its own, which implies, again, that we need to have a framework of governance in place as we move through this revolution. And that's something that we're also working on. And I think it's something that will eventually will become as an important issue for United Nations and collectively for the world.
Great, thank you. That's all the time we have for today. Thank you, Al, and thanks to everyone for attending and for sending us your questions and comments. We do hope that you'll stay tuned for future topics in 2018 as we continue to explore this area of artificial intelligence. All content and materials included in this online event are the property of APICS and are protected by the United States and international copyright laws. All rights are reserved.